So the next thing that I want to discuss is the relationship between the two different formulations of quantum mechanics. So far, the formulation of quantum mechanics that we have seen is known as the Schrödinger representation or Schrödinger picture. And there's another representation or view of quantum mechanics which is called the Heisenberg picture. And so now what we're going to do, we are going to discuss how these two things are related. So in quantum mechanics, the observables are really inner products. So inner products of, say, chi, some state, and some observable acting on, say, some other state, say, psi. So these are the things that we measure experimentally. And this is a function of time. And according to our formulation of quantum mechanics, O is an observable, therefore it's given by a Hermitian operator, and it usually doesn't have any time independence. So this is usually time independent. Whereas the time dependence is carried in the wave function, say psi, chi, etc. And that the time evolution of these wave functions are given by the time dependent Schrödinger equation, which is written like this. So now if I look at this object, which is saying that this is an inner product which depends on time, we can figure out another way of formulating quantum mechanics. And the way to go about this is like this. Remember that if I look at this inner product, say psi, O, which is an operator, phi, at some time t, of course this means that nothing but psi, which depends on time, and then O, which doesn't depend on time, and phi, which depends on time. So, but we introduce the time evolution operator, which evolves the state at time 0 to the time t. So we now explicitly is writing the time evolution operator, right? The time evolution operator is the formal solution to the Schrödinger equation. So then what we can do is that we can then take this guy over here. Then I will have psi of 0 and then u dagger of t O hat u of t psi of 0. And now what we can do is that this is an operator. We can define it as O hat h times t, because now this operator depends on time, and this h stands for Heisenberg. So what we can say is that we can take a formulation of quantum mechanics where we specify all the states given at some time, t0 say, but all the dynamics of the theory is given by time-dependent operators, say O, say H, where each of these operators are related to the time-independent operators that we knew in the previous formulation by this relationship. So this I'm going to call OS to emphasize that it was the operator in the Schrödinger picture. And it was time independent. So in the Heisenberg picture, it's the operators which are evolving in time and therefore they're dynamical objects. So you might ask, what is the equation of motion? So we can figure out the equation of motion for the operators. So suppose that the operator O has no explicit time dependence. So what I mean is that suppose the operator OS doesn't have any explicit time dependence. Then the operator OH of t is given by U dagger of t applied to O of S, U of t. And then, we say what is the time derivative of O? So then, according to its definition, we are going to use the Leibnitz rule. So first we take the derivative of u, and then there is os and times u. First we take the derivative of u dagger, and then o doesn't depend explicitly on time, so there won't be any derivative term for that. So then we are going to have o dagger, u dagger, o of s, and then d of u of d of t. Now let's look at what d of u dagger, d of t is. Remember, u d dagger is nothing but e to the power plus I by h bar h of t. And therefore, if I take the derivative of this, what I get is e to the power I by h, big HT, times I by h, big H. And similarly, d of u, d of t can be written as minus I of by h bar times h, e to the power minus I by h bar h of t. And therefore, if we look at this, this becomes d of oh dt is going to be, this will give me, this is basically just u dagger. So we get u dagger, then I by h bar, h times o, and then we have u, and then we have minus u dagger, o, minus I by h bar, h of u. So if I factor out I by h bar, we get u dagger h o, the commutator, times u. But of course, what we can do is that we can then write this as by 1 by h. And here, let me just do it explicitly. The commutator of h and o is just ho minus oh u. So what we can do is that we can then write u dagger h times o, but between h and o there's a number 1. So that number 1 can be written as u times u dagger, because u is unitary, u dagger is its inverse. So this is 1. So then we get 0, and then u. And we can do the same thing for the second term. This is u dagger o, u dagger times h of u. So what is this? This is I by h, and this thing is simply the Hamiltonian in the Heisenberg picture. And this thing is the O operator in the Heisenberg picture. Sorry, I forget to put the carets. And then we get O and H, or in other words, I by H bar, H of H, O. But you see that H bar, H is, the Hamiltonian in the Heisenberg picture is e to the power I t by h bar, big H, acting on H in the Schrödinger picture. This is also in the Schrödinger picture, e to the power minus I t by h bar, h of s. But this thing and this thing commute, so this guy will cancel this guy. So the Hamiltonian in the Heisenberg picture is the same thing as the Hamiltonian in the Schrödinger picture, and we might as well just write it as h. So therefore we have found that the time derivative of an operator in the Heisenberg picture is given by I by h and the commutator of the Hamiltonian of the operator O in the Heisenberg picture. And this is the Heisenberg equation of motion.